Alright, in today's tutorial I will be showing you how to make a realistic Saturn. So I'm starting out already with a spherified cube, and I'm in cycles. I'm not going to go through all of the details. I've done this in previous videos. So grab a sun lamp, rotate it 70, or no, sorry, rotate it. No, okay. Rotate it 70 degrees, or 75, maybe 80 degrees. Yep, 80 degrees. And then set the angle to uh, okay. Set the sun angle to 0.05609 degrees. And then set the strength to 15.05. Because this is the angular diameter of the sun, as seen from Saturn, and this is the amount of solar radiation it receives, watts per meter squared, 15 watts per meter squared. And so now I've got this. Okay, let's worry about the we'll do the atmosphere and rings later. We'll just work on the surface for now. So for the base color, go an image texture, and I've already got 16K texture in here. Plug that into the base color. And turn the specular and roughness all the way down. There we go. Okay, now set the projection method to sphere, and grab a geometry node and plug position into vector. And you'll notice something's a bit off. Actually, here I'll make it a little bit more visible. Plug in a gamma here and set the gamma to 2. There we go. When we use position in the vector, it's all wonky. But with generated coordinates, it's correct. But we still want to use position. I'll show you how to deal with this. Grab a vector math, add 1 to x, y, and z. Actually, you know what we can do? Grab a separate x, y, z and a combine x, y, z. And then what we can do is we can just add 1 to all of these channels individually. And then duplicate this, plug this into here. Actually, no, we don't need to. Grab another vector math node and set it to scale. Scale this 0.5. Now it maps correctly. That looks pretty good. I'm just going to tidy this up a little bit. So, okay. So group this texture with the gamma node, and just put the vector here somewhere in this color output, spaced nicely. I think that's probably fine. Okay, you want to call this position in. Okay, so this is position in, and this will be our Here, set this to vector. This will be called diffuse out. Make a new output and call this metallic out. Make a new one called specular out. A new one called roughness out. And finally, displacement out. And then we'll call this ground or surface attributes or parameters, whatever you like the sound of. Okay, so we've got our diffuse out, we've got a metallic out. We'll plug the specular and roughness into here. Right now it's not going to do anything, and it shouldn't do anything because these are all equal to 0 right now. And we're going to keep it that way for now, but if you have any maps that are for any of these, obviously you can use them in here. And yeah, you should control your color stuff inside of the surface attributes node. You shouldn't really control it out of here. I mean, you can if you want, but I'd recommend keeping it all in the surface attributes. Okay, so now that we've got this, we'll group this. This output will be called position out, and this input will be position in. This will be called sphere projection. Okay, that's good. We've got sphere projection, and we've got our surface attributes. We've got our principled BSDF. Okay. Oops. Updating images. Okay. That's good. And now, what you want to do, let me just copy this value. Sorry, I'm referencing another blend file of mine. That's why it might take me a second. Set the dimensions on the z-axis to 1.80407 meters. And then Control A and apply all transforms. There we go. Looks pretty good. It's nice. I'm gonna hide these. Okay. We want to duplicate this. Duplicate the material. We'll call this atmosphere. This is going to be a little bit of an advanced atmosphere compared to my other one. It's pretty much, it's basically Samuel Krug's atmosphere with a few changes. So, get rid of all of these. And there's one thing we have to make, because if you remember from the last atmosphere tutorial, in the density function, it took the radius of the it took the radius and then subtracted the planet radius from the volume of that atmosphere. But our planet radius is different along different axes. So we're going to have to make a special node group that tells the length the radius to change depending on the axis for our planet dimensions. So grab a vector math and just group it. Set the output to a float. Call this planet radius bracket x comma y comma z bracket out. Actually call this node group planet radius comma bracket comma bracket x comma y comma z bracket, and then just there we go. Plug the position into the first vector. Okay, turn the second vector into a float and make another vector after that. This will be our planet dimensions in meters. The second one will be our planet radius in. Oh, right, I forgot to put in after these. I like keeping it like that. You don't need to, but I like to. And then we'll have our position in. Okay, so you grab a object info node, put it right here. Grab a vector math divide. We divide this by 2 to get the radius from the planet dimensions. I mean, you could just type in the radius into here, but it's easier just to type in the exact dimensions, and this will do the math for you, which is always nice. And then you want to subtract this location from the position in. And then you want to divide this from this. And then you want to grab the length from that. And then multiply this. Multiply this by the planet radius in. So let's grab that, put it in here, make sure to remove the M so it doesn't muck up. And there we go. We've got our planet radius, X, Y, and Z. Okay, now for the density function. Which part do we want to do first? Yeah, okay. Okay, so grab a math subtract node. Put this into here like this. Actually, I'm going to plug this into the volume. Grab a displacement. Plug that into here. Set the height to 0.01, mid-level to 0. Go to the material settings and do bump only. Oops, displacement only. That's what I meant. There we go. And you can start to see some volume here, which is always nice. Okay, but we're going to need to create a node group. So, oh, no, don't make that bigger. There we go. Yep, so call this radius out, the output, and then this will be our planet radius. So plug that into the subtract here. And into the planet radius in on our X, Y, and Z one. Now you want to combine X, Y, Z, plug the vector into the planet dimensions. And then just put all these into here. There we go. Group that remove these X, Y, and Z inputs. Just grab this, which will be our dimensions out in meters. Or I guess we could say, planet dimensions out. There we go. And this will be our planet dimensions. Okay. And you want to divide this by the atmosphere thickness, which is 0.01, or we have set here. But instead of having to change this and then change this, which is just a pain, what we can do is we can make a node group for atmosphere thickness. So call this output thickness out. And plug the height into here. Call this atmosphere thickness. Make this a bit bigger so you can see it. There we go. And plug that same one into the divide node. And there we go. Good. I'm gonna move this over a little bit. Okay. Actually, I just realized something. Instead of calling this displacement out, call it height out, rather. Okay. Also call this mesh atmosphere. Make sure this is called atmosphere 2. I forgot what's that called. The mesh data, I guess. Just make sure it's all named atmosphere, so you can tell what it is. Okay, and then multiply this by about 25. Sounds good. Actually, I forgot one thing. Grab a maximum, set it to 0, place it after the subtract, and yeah, after the subtract, or between the subtract and divide, set it to 0. Multiply this by 25. Use this as an exponent, and use 0.5 as your base. So it's 0.5 times radius minus radius divided by atmosphere thickness times 25. So there we go. And then multiply this by 256. There we go. It's coming together. I'm going to move this position, and I'm going to group this. That already has the name of position in, so that's good. This needs to be a vector output. I mean, another one that's the vector output. This will be extinction out, and this will be color out. Actually, I'm just going to call this atmosphere color out and atmosphere extinction out. There we go. And this will be our atmosphere density function. Okay. Now grab an emission node and an add shader, and grab a volume absorption node. Because volumes also absorb light, and typically volumes absorb the same color of light that they also scatter. So I will show you what I mean by that in a second. Let me just plug this into the density of this and plug this into here. Actually, put a multiply before this as well. Just multiply it by 1. Oh, it's not 1. There you go. Multiply that by 1. Put a value node here. And this will be our atmosphere density. This will be our density out. Okay. And multiply this by 1 as well. This atmosphere extinction out. And then this will be hold on. We could, this is the absorption amount. Call this the absorption amount. And just call this absorption out, I guess. I don't have a better name for it. Okay. Now grab a vector math scale. And we're going to scale this by an RGB value. Right. Okay. Plug that into the color. Vector math. We normalize the color. And then we use a length. So we're left with this. Looks good. Oh, right. I was going to show you the way volume absorption and stuff works. Let me plug this into the strength so I can show you. So typically volume absorption, or typically a medium scatters and absorbs the same color. So if I set this to blue, hold on, we got to make this a subtract and then subtract this from from 111 in here. And that should be, I'm sure it is working and I'm just blind. Oh yeah, you can see a little bit of red being reintroduced as we make it blue. Kind of neat. There, we'll normalize this again. We still need to subtract it from 111 and plug this into the color. Okay. So set this to about 0.7 and group it. Call this color out and call this absorption color. This for density. Here, actually, I'll call this atmosphere absorption amount. And this one will be atmosphere absorption color, just in case you have other things in your scene that also use absorption, like different volumes. Okay, so we've got our absorption color, which we need to subtract from the 111 vector. It just inverts it. So now, if we do blue, you get blue because we're inverting it again back over here. So we've got our color out. And right now I'm going to set it to like a right here. So hue of 0.6 and a saturation of 0.565 or 0.535. 0.5. Okay. Hue of 6, saturation of 0.5, and value of 7 or 7.7, sorry. Okay, now we want to work on the atmosphere color. So also scale in RGB by the density. And this one will also be very light blue, probably around 0.6 as well, and maybe about 0.3, 0.35, maybe 0.4 for saturation. Yeah, there we go. Okay. And we will group this and call this color out. And this will be our atmosphere color. Or atmosphere scattering color. Yeah, there we go. That's good. Okay, so we've got this density function, but we've also got no shadow, which is not correct. So we need something called a ray sphere intersection function and a few other things, but I'm going to grab ray sphere intersection function. I'm going to append one. I will put a drive link in the description though for the ray sphere intersection function. If I can find it, sorry. No tree. Ray sphere intersection function. Okay. I got this ray sphere intersection function. And I'm actually going to, well, I'll copy this because I don't want to have to try to find it again. But I'm going to delete the sun, go to File, Clean Up, Recursive, and Unused just to make sure. Okay, and I'm going to append that same anisotropy scalar. You know what, I'll just put in a new anisotropy scalar in the drive. But we want an anisotropy scalar as well. And I'll just set this to like 85 for rotation. There we go. So we need to plug the position into the position in, set the radius to 1 or planet radius. And for the direction, we need this light direction node. It'll be in here if once you append the anisotropy scalar. Plug the direction into there. So we've got a discriminant, got a vector close out and vector far. So okay. Here I'm going to bring this up. Bring this over here. There we go. Okay, so grab a vector math node and group it. Call this first input position in. Call the second one our step vector or sample vector here. We'll make the step vector right now. We already basically have it, but you subtract the vector close out from the vector far out. There we go. And plug that into the step vector. Let's call this atmosphere light computation. And we'll also plug in the position in. And then we multiply the color of the emission with this. Okay. You also want a float value, which will be samples in, make a new vector, and then make another float at the very bottom. Call this counter in, and this one will be atmosphere extinction in. I'll just make this bigger, make this one bigger too. And then this one will be just lighting out. Okay, and then group this one as well. And you want the same thing. So we need a position in, we need a step vector in, we need an atmosphere extinction in, and then we need these two float values. We need our samples in and our counter in. Okay, and then delete this. Plug the position in, step vector, samples, extinction, counter, all of that plug into here, and then plug this atmosphere extinction into the lighting out. Set your samples just to like 8. Actually, let's do that outside of it. Set your samples in to like 8. And then for your counter, you need a white noise texture and plug the position into the vector. There we go. This will be a light sample. And there we go. Okay. So duplicate this, plug the step vector in, samples in, and atmosphere extinction in to these, and we want to rename these to have out at the end rather than in, because it's an output. First part is a bit tedious, but then it gets a bit better. So grab a vector math add. You want the position. Grab a vector math scale. We'll just set this to 0.125 right now, just because there's 8. Okay. You want to add the step vector in scaled by 0.125 to the position, which will be used for our atmosphere density function. It'll be used as the position in. There we go. You then want to grab the length from the scaled step vector and scale the atmosphere extinction out by the length. So let's see what's going on. Hold on. Oh, I know what we did. For this radius in, delete the planet radius and grab our planet radius x, y, and z. Plug that into here. And then grab the planet radius, plug that into here with our dimensions. Plug that into here as well, and then just plug in the position. And then it's that plus the height of our atmosphere, which is just our atmosphere thickness. Plug that into there. There we go. Okay. I was wondering what was going on there. So keep this atmosphere extinction plugged in here, and then we just want to add this into here, because what this is doing is it's an iterative function. So we're basically just adding the extinction data over and over and over again. Main part is done. We'll just work on the samples and the counter. So grab a math power node, set the exponent to -1, plug the samples into the base, grab a multiply, and then add. From the counter in, we add 1, and then we multiply this power from the samples by the counter plus 1. Okay. Make a new value. Let's call this like shadow quality or something. It's not exactly what it is, but I don't know anything better to call it. And then power. This multiply goes into the base, and then exponent of 4, power of 4, which is our shadow quality. We're just going to plug this into here right now, actually. Okay, we grab another power, plug the exponent into here, plug this into the subtract. And we grab a multiply, and we multiply this power by the counter in. There we go. And then this position out back here is just this add node. And then for the counter out, it's just this counter plus 1. So it's counter in, counter plus 1, counter out. And depending on how many samples you have, these light samples, we're going to add 8, maybe 10. We're going to add 10 light samples for this tutorial, but basically it says this white noise texture. We've already got this white noise texture. It's going into the counter in, and then it's counter in, white noise texture, counter in, plus 1, counter out. And then when we iterate this over and over again, it'll then be that counter plus 1, out, plus 1, out, plus 1, out, for some progressive rendering. I'm not the one who came up with this. It was Samuel Krug. Very cool guy. I will link his, actually I think I linked it in the last tutorial, but I will link his YouTube channel in the description of this video. Makes some amazing stuff. Okay, so now we're just going to iterate this light sample. So position out to position in, step vector out, samples, atmosphere extinction, counter. I'm just going to duplicate this. And duplicate it again. And then I'm going to duplicate all of these, so we've got 10. And I'm going to move this over. Okay. So we duplicate all of these. So now we've got 10 of them. We just chain these last ones up together. And we're left with this. Our shadow is on the wrong side. So you grab a separate XYZ and a combine XYZ. Grab a math power and plug the X, Y, and Z into their own power exponents with a base of 0.5. This just inverts the channels because X Y and Z are R, G, and B. So it's just inverting the R, G, and B channels. Let me tidy this up a little bit. Okay, good. Then you grab a value. This will be our, here I'll call this extinction out. Okay, this will be our atmosphere extinction coefficient. You duplicate this and instead add the extinction into the X, Y, and Z channels. Okay. So this is an extinction of 0, which is what we had before. I like 1, you can go up to 2 as well. Yeah. Okay. Saturn's atmosphere has a little bit of anisotropy though, so we're gonna add that right now. Oh yeah, we can bump the sample count up to 10. Also, I'll show you what happens if we lower the sample count. There's 3 samples. You can see it gets less precise. It's like curl fields. You need more and more iterations for it to be more and more precise. 2.4 samples, 2 samples, 1.5 samples, 0 samples. So we added 10, so I'll do 10. Okay. Right, that anisotropy scalar. If I can spell. Okay, we grab our density function and we scale the scattering color by our anisotropy scalar. And if I set this to like 0.9, I mean that's not a realistic value, but you can see what it's doing. Anisotropy is just the ability of a material to change its physical properties or assume or change its physical properties along different axes. So if you were to look at a rolled steel sheet, it would have anisotropy because you can kind of see the light being stretched all the way across the beam, which is anisotropy. 0.4 to 0.5 is a more accurate anisotropy value. But what we'll do is we'll grab a value node, sets to 0.4 or 0.5. We'll call this anisotropy out. And then this will be our atmosphere anisotropy. Okay. We are done the atmosphere, and we will move on to the rings. Okay, so for our rings, grab a circle, give it 512 vertices or more. I don't know why you would go any higher. And go to its dimensions and set its X and Y dimensions to 4.17042 meters. And apply all transforms, and then fill in the face. Then make a cylinder, also with 512 vertices. And set the x and y dimensions to 2.17042 meters and the z dimension to 0.035 and apply all transforms and click on the rings. I'm also just gonna call this rings, call the mesh data rings. Add a Boolean modifier. I'm gonna hide this. Add a Boolean modifier fast object, set it to the cylinder in the middle, then apply. Then delete these two edges and then bridge these edge loops. And hide the cylinder and render. There we go. So everything here is obviously not accurate to scale, but proportionally accurate. And we'll call this rings. Okay. So for the rings, grab a geometry position. There you go, that's good. Okay, so geometry position, and then grab a vector math length. Then you want to grab a math add node, multiply this by a small number, and subtract 0.5, just because the way procedurals work, and plug in a noise texture. I'm just going to make this a little bit more visible so we can see what we're doing. So bring this up to about 128, detail of 10, roughness of like 0.8, and then bring the multiply down to 0.25. Should be good. And then this is used as the vector for our ring texture. A good source for planet textures is solarsystemscope.com. I'll link it down in the description. But I will open up my ring texture. And voila. Not quite done yet, though. Does look good, though. Wow. Okay, I'm going to hide the atmosphere temporarily. Just a slightly smoother viewport. Okay. So drag off this color and grab a normalize. This normalizes the color. And then you want to scale this. Actually, here. So grab a color. Grab the color from this and subtract it from 1. So you're left with this So we want to subtract it from 1. Don't subtract 1 from it. Subtract it from 1. Then grab a power. And I like to use 50. Actually, maybe 30. Let I see what 40. Okay. I like to use 40 to 50 from, actually, no, I can, yeah, 20, 30. Okay, yeah, use about 30 for the power here and scale the normalized color by that. And then scale this by an anisotropy scaler. Set your ring anisotropy to about 0.8, I would say. And we'll just grab a value. Sorry, okay, grab a value, set it to about 0.8. Call this anisotropy out. And this will be our ring anisotropy. This is for the shimmer. I've used this technique in my procedural ring shader as well, which I will link down in the description. Or I'll just see if I can put it on the end title or end card screen. Plug this into a translucent BSDF. Maybe 50 actually. No. Okay. And then mix that. Oops. Mix shader. Mix this with a transparent BSDF. Also with a power wrenching off of the subtract as the factor. So you can use 20, 30 maybe. Yeah, I like 30 because we get dense shadows. 50. Yeah, 30 seems to work quite well. You can see that ring shimmer looks quite nice. Okay, and then to this translucent, we will add a diffuse and plug in the normal ring color into the diffuse. And let me just make sure I didn't miss anything. There you go. We got rings that shimmer. So I will unhide the atmosphere. Update images. There we go. We're done the rings, but there's one thing you might have noticed. The ring shadows do not occlude any light in the atmosphere. There's the shadow, and then there's the emissive atmosphere over top of it, which does not, it's not that great. So, to fix that, we need something called a ray plane intersection function, which I will also link in the Google Drive below. So let me just append mine quickly. Ray plane intersection function. Okay, so we grab our ray plane intersection function, and you know, I'll plug this into the surface. There we go. Okay, so our ray origin is just the position vector. Plane normal is just 1, or the... You could also substitute that with the rotation of the rings. Plane origin should be at 0, 0, 0, 0, 0, sorry. And the ray direction will be our light direction. So now, let me pin this. Now you can see that we've got basically a plane that rotates with the light direction. So we use this for our ring texture. Actually, sorry. We need our planet radius, which I will get planet radius here, and then we'll grab the planet dimensions. Put it, where did I end up? Okay, put it right in here. And there we go. So I'm gonna bring these out a little bit. Okay. in the rings, we did add that extra detail into the rings here with this noise texture. So we're going to do the same thing. I'll just copy these and paste them right about here. Just add this to here. Oh, sorry. Get rid of this. Put that right in here. So we're adding to this, and then we use this as the vector for our ring texture. But you can see as the sun angle changes, it repeats the textures because we haven't defined the bounds of the texture. I sadly only learned how to do this yesterday. But here, let me delete this. You go ahead and multiply this by our discriminant. Oops. Multiply by our discriminant. And then you multiply this by the planet radius with a less than 2. And now, okay, we got that part working. And then you just multiply this by whatever shadow density you want. I'll do 64, should work. Okay, and then we need to use this as the exponent of a power, which, like I've said, inverts it just inverts it when you use a base of 0.5 and then use your function as the exponent, it inverts that function in a way, which is nice. And then into this emission, you just scale it by this power. And I'm going to plug this into the volume so you can see what it does. Updating images, and there we go. It now properly occludes light in the atmosphere, which is awesome. So pretty accurate rings. Almost accurate atmosphere. Look at that. Oh, that looks so cool. Here, we'll look at it in the viewport, or a bigger viewport. Yeah, look at that. So you can see the where the shadow is being cast on the rings. You can also see the shadow or atmosphere shadow, or the light passing through the absorption, hitting the edges of these rings, or edges of the shadows on the rings, which is super nice. And you can see we got shimmer underneath the rings from the anisotropy. You can get some really good renders if you just take some time to set up a nice angle like this. This looks quite nice actually. So we're going to render region. And yeah, that is how you make Saturn in Blender. So just obviously, like always, have fun messing around with the values, like the anisotropy and the extinction coefficient. And actually, I want to show you what happens if you increase the extinction coefficient a little bit. Kind of imitates like limb darkening. I mean, I would probably just make my own part in the density function for limb darkening, but you can definitely just increase the extinction coefficient a little bit. If you increase it a lot, looks interesting. It's a bit too much. Yeah, so it's super easy to set up a good looking Saturn. When you configure Blender properly, like with something like this, all these light samples or the atmosphere light computation. It's very interesting. All right, I'm gonna leave it at that. Yeah, have fun messing around with the atmosphere and rings. Bye.